So hello, students. Thanks for being here today. This is the pathway presentation. You'll be hearing from Dr. Constantine Balanis in the electromagnetics area, and then later you'll be hearing from a faculty member in the electric circuits area. But without further ado, we're going to pass it off to Dr. Balanis. So thanks for being here with us. He's an awarded and fantastic faculty member, world-renowned, no joke. It's the real deal. So we appreciate that he's here. And thank you for presenting today, Dr. Balanis. We're
Thank
in
you
awe
very
of your
much.
presence.
I
You're a very
appreciate for
impressive
the
man.
introduction, and it's good to see you all. And today we're going to talk about electromagnetics, pathways in the electromagnetics area. Obviously, this is my name, and if you want to see a picture of me on the 7th tee box of Pebble Beach. That was in 2013. Okay. Now, let me take this out of here. Yeah, what is electromagnetics? Electromagnetics, we have statics and dynamics, and the study of charges, electromagnetic charges in motion or at rest. Rest is the statics, and we covered it at ASU in the course Triple E 241. All electrical engineering students have to take. And the second course is the time varying. The dynamics is the 341. EM electromagnetic measures have to take it. The other ones highly recommended, at least from my point of view. Electromagnetics is really described by four basic equations, vector equations. They refer to them Maxwell's equation. I'll talk a little bit more about Maxwell in a minute. There are special cases that all of you taking courses in electrical engineering have been exposed to: circuits, Kirchhoff's laws, geometrical optics, physical optics. Those are really special cases of Maxwell's equation that do not use all the terms in Maxwell's equations. I'll show you that in a minute. And James Maxwell, of Scotland, lived in 1831 to 1879, not many years, to be exact, some 48. Here's Maxwell, and this is a statue of Maxwell in Scotland. And very recent means within the last couple of years, a student of mine at ASU, got his PhD at ASU in around 2021, 22, 21 or 20, I guess. Subramanian Ramalinkan. He was in UK, and he took a side trip and visited the home of Maxwell. And right on the outside there are Maxwell's equation. Here they are. Here's a plaque of Maxwell's equation. So he took some pictures, sent it to me, and here I am showing it to you, thanks to Subramanian, and I know a lot of the staff knew Subramanian. Those are Maxwell's equations in integral form. They're also in differential form. Those are they have all the terms now in circuits, physical optics, geometrical optics. We don't use the last term. It's usually small compared to the other terms, so we usually leave them out. But in full wave applications, we use all the terms. And same thing with the second equation. The last term is usually small, and we leave it out. Why electromagnetics? Well, let me just tell you from a personal point of view. I taught 51 years. I worked for NASA for 6 years. Started in 1964 EM is the basis of electrical engineering. Don't let anybody tell you otherwise. Fundamental challenging problems in many areas of electrical engineering, including just few of them: wireless communication, packaging, stealth technology. Be able to use to solve, complex problems, practical problems using, this is what I'm referring here, full wave techniques. Treat the problems as distributed devices, not lumped elements like we usually do in circuits. That's why circuits approximation to Maxwell's equations. Modeling, simulating devices using what we refer to full wave solvers. Those are analytical methods, software associated with them that account for all terms of Maxwell's equations. Okay, and other. Here are some devices. We're all been through this. Going back to 1983, actually, I actually started in 1973 at Motorola, but we went public in 1983. Some of the cell phones, where initially the antenna was outside the device. As you can see here, the StarTech, I used to have one of them, the first one, and really the second one as well. And then eventually they put the antenna inside the device. Maybe didn't look nice to have it outside. Also, they used to break. So accomplish both purposes. Exposure and the device, and also reception. Why study electromagnetics? Again, analyze, model, design EM type of problems, antennas, RF, microwave circuits, fiber optics, electronic packages, electromagnetic interference, electromagnetic compatibility. Here are some a photo of a device, a system, I should say, for wireless communication, substation. Here's a full packaging circuit, if you wish. Laptop, cell phone, we already talked about. And not to remiss, stealth aircraft. To be successful in electromagnetics related courses, what you must take? Math, physics, circuits. All areas of electrical engineering depend upon those three areas, especially mathematics and physics. Electrical engineers are, EEs, I should say, are engineers, not technicians. So you must know mathematics, physics.
Oh, Dr. Balanis, you're muted.
Oh,
What? You're muted again now.
do it again.
Yeah. Oh, you did it again. I think it's got something to do with the
I'm
arrows.
supposed to mute you.
I promise it's not me muting you.
Okay, can you hear me now?
Yes.
Yep.
Unfortunately, huh?
Yeah.
Yes. Okay, now so we having a problem. Okay, yeah. What are prerequisites? Again, we already mentioned Triple E 241. All electrical engineering students must take this course. It's required. Circuits and physics. Physics course lecture as well as a laboratory that goes with it. So this is kind of description what Triple E 241 covers. Actually, mostly covers static, type of a problems, but also time varying or time varying type of a problem. And boundary value problems, dielectric, magnetic materials, again, you utilize Maxwell's equations, and when you use differential equation, you have a boundary, associated boundary condition that you must apply to solve them. Again, repeat, prerequisite, EEE 202 circuits, as well as a physics course. And the other course, which is required for EM majors, is the 341. But from my personal point of view, all of you in electrical engineering, I think this is an excellent course to take. It's more applications oriented. It applies to time varying fields. So time varying electromagnetic fields, waves in homogeneous, stratified media, nonlinear, transmission line, waveguides, resonators, radiation problem like antennas and so forth. It has a lecture. It also has a laboratory. Again, personal recommendation, suggestion, we called. This is very, very important course, and I highly suggest it. People, especially in communications, in solid state, I think this is an excellent course to take. And it, of course, as mentioned already, requires that you take 241. Of course, all electrical engineering students have to take 241. Okay. Senior elective courses. We have a plethora, as Howard Cosell used to say, of senior elective courses. One of them is a course in antennas, 400 level. And this are some of the topics that we cover: fundamental parameters, dipoles, loop antennas, arrays, smart antennas, microstrips, antenna measurements, and so forth. Very, very applications oriented. Microwave, very, very, very important. Again, 445 talks about impedance matching, measurements, you name it. All communication systems are nowadays in the microwave area. So this is most important course. Fiber optics, another very, very, very important course. All those during my tenure at ASU and before, very courses that many students used to take as electives, senior electives, if you wish. Prerequisite, 341. You have to take the second course in electromagnetics, the undergraduate. Graduate courses, again, to repeat, plethora, many courses. Not all of them taught on a yearly basis, but many are. We have as a good of an array of graduate courses as any school in the United States. I'm telling you, I know. There are some even on the 600 level. I know during my tenure, 38 years at ASU, we introduced them, we taught them, not on a yearly basis, some of them, but were taught, okay? Graduate school. If any of you have any aspirations to go to graduate school, I highly recommend it, and you do it without taking a leave of absence. Do it while you're poor and stay poor and finish, and then you're done. Master's degree. Yes, somewhat specialized, applications oriented. And again, often the most marketable degree for pursuing a career in industry and government. Yes. Nowadays, because the communication systems are more exotic, more complex, more precise PhD. Definitely, if you are having aspirations to go to teaching, like I did eventually, it requires that you have a PhD. It's kind of specialized in a specific area, but you become, if you wish, quote unquote, expert in that particular area. It's required for research development, and I mentioned already, required for university positions. Career opportunities, many opportunities in academia. I already mentioned, you need a PhD though. What do you do? Well, obviously teaching is one, but nowadays you write proposals and get funding from outside to support students, graduate students, perform research, write, publish papers, do maybe even consulting as time permits. Industry, again, opportunities for industry position with a bachelor's, a master's degree, PhD. Again, many different areas that require or are EM related antennas. Again, I mentioned RF and microwaves communication, radar, remote sensing, fiber optics, electronic packaging, job opportunities. Let me just tell you, we are here in the Phoenix area. One, it was, and maybe still is, the second largest high-tech area outside of Silicon Valley. One of the reasons why I came to ASU back in 1983. We have all companies, you name it. I list some of them here. Motorola was the largest employer when I came here in Arizona, not in the Valley, in Arizona, 19,000 people. I did consulting for them. They sponsor work with me here. We had many students for Motorola taking advanced courses, advanced degrees, especially masters at that time, even PhD, Honeywell, Intel, Raytheon. I'm looking here. Well, Boeing, you know, it used to be McDonnell Douglas here. It's very close to my house. General Dynamics, you name it. Government. Again, I worked for NASA for 6 years, back in the 60s, 64 to 70. Position, the Army, the Navy, they were big supporters of mine. In research here at ASU, we had a consortium of industry and government. We used to call AHI, Advanced Helicopter Electromagnetics. They sponsored work with me for 28 years, starting 1990, January of 1990. We had members were NASA, Army, the Navy, the Air Force, let's see, Aerospace Corporation. We had companies, other companies, McDonnell Douglas, and so forth, Boeing, I mentioned. Also, we have a number of faculty. Some of us are emeritus now. Professor Eberly came here in shortly after I came to ASU. He's still a full professor, excellent teacher. There's me, now Professor Emeritus. Professor Riza there, he graduate University of Michigan. Michigan beat Ohio State in football. Okay, and I'm an Ohio State graduate. I shouldn't say that very loud. Here's another Michigan graduate, Professor Palais. He was probably, not probably, was the most senior faculty members in electrical engineering when I came. Okay, devoted his entire life basically to teaching, especially ASU, excuse me. Professor Pan, I think recently he became Professor Emeritus as well. And Professor Trikopoulos, another Greek. He's associate professor, joined the faculty. He's also proud alum of the Ohio State University. They won the national championship, of course, the other day. I need a smile from all of you, if you please. Okay, congratulations or whatever. We have a number of books written by faculty. Of course, this me being one of them. This is the antenna book. The first one was the second edition. The second one there is the fourth edition in color. This is the Advanced EM book, which I wrote when I came to ASU. First edition in 1989. I have a small book on smart antennas, co-authored with one of my former graduate students. Handbook on antennas. Fiber optics, authored by Professor Blain. This is a book authored by Professor Pan. And last but not least, my advanced EM book, the third edition, even have my name on the title. How about that? Antenna facility. This is, we built this one. It became operational in mid-1980s, 95, 86. At that time, and maybe still is, the second best facility in the U.S. in university. The only other university that had or has had such a facility was Ohio State University, and they've been in that business going back to the late 1940s. Here we are, here we at ASU built this facility. I joined the faculty in 83. We built it, became operational 85, 86. Still in operation, used for education classes as well as research in support of projects. So we call that the electromagnetic anechoic chamber, EMAC, antenna radar cross-section measurements. And from personal viewpoint, why electrical engineering, why electromagnetics, why NASA 6 years, why West Virginia University 13, why ASU 37.5, why golf? Yes, golf. I'm not very good at it, but I do go play. You can go to YouTube. There was in 2023 interview in my office in the Goldwater building. It's a 72 minutes, and if you go to YouTube, there's Legends of Electromagnetics, Professor Constantine Balanis. You will see it. It'll put you to sleep for sure. If you have a sleep apnea, this is a good remedy. There's a coin that the Antenna Propagation Society of IEEE, they named me. I was one of the first ones. This was the interview that was conducted in my office in the Goldwater building. It's coined Legends of Electromagnetics. And thank you very much. And I will take any questions if I can answer them. And then, but not least, also in the, this is the birthplace of golf, St. Andrews. I had the privilege and the opportunity and to play there, and then met a couple of people on the train going there. They were from Texas, LTV Corporation. We played a round of golf. They get the person to the right. There's another colleague at the university. He and I stayed there, St. Andrews, that night, had a nice dinner, and then we went back to Edinburgh. So that's it.
So despite the excessive Ohio State references and my personal exception to the use of the word plethora too many times, I recommend myriad next time.
Do you see this maybe the Ohio? Let me put a little higher.
Well, we joke, we thank
Oh,
you.
yeah,
I did
okay,
put
I'm
the
sorry. Okay,
I put the
let's take some
video to
questions if there are any questions.
yeah, and I did put the video link in the chat so the students can watch it later if they'd like it.
By the way, let's just make one comment. Okay, I'm a professor emeritus. I had the opportunity to work with the best faculty and the best staff. And you see some of the staff right there. I worked for 3 different places. The staff at ASU cannot be matched.
Well, now I can't make
Sorry.
fun of you. That was just too nice. Now I have to be nice to
Yes,
you back.
yes.
I
Well,
so I have a question for you for the benefit of the students. When we're talking to students a
A
lot,
little more loud. I can't hear the beginning.
you can't hear me?
Yeah,
No
no,
one has
yeah. I
ever
don't know,
said
but
that
now
before.
the audio is no. It's on from my side. Yes.
Yeah, I think it's a you problem.
Yeah, yeah. It's my problem. Yes, thank you. You're
Can
very nice.
you
Yeah, I gave you a
talk
nice compliment. The least you can do is be complimentary also. You see, that's what I'm saying. What did I say? Best staff that I have worked with. I'd be surprised if any institution, any company, you'll find such a staff. Okay, I'm done.
I'll try and think of a compliment by the next time you come around. I'll work hard on that.
Yes,
Uh, can you talk to students about 241 and 341 and
yes.
tell them to just get through 241? It's okay.
The 241.
Yeah. Everyone hates 241 and then they shy away from 341. But the
Yeah.
students who stick it out through 341 say that it's great. So can you talk to students about why 241 might be kind of hard at first and why they got to stick through it?
Yeah. Well, electromagnetics probably again. We have to tell the truth as it is. It involves the vector fields, vector, and you need to be good in mathematics. You have to take courses like vector analysis, vector calculus, whatever you want to call it, complex variables, differential equations. Yes, it is a tough course. It may be at the beginning, it looks like it's kind of abstract, but I promise you, I go back to 1960s, 60 to 64 bachelor's degree. I had a professor teaching electromagnetics. I took, at that time, both courses were required. And I mean required, you have no choice, anybody. Professor Ebert. A lot of the students didn't like him. He was tough, but he was good, excellent. So yes, 241 maybe look like maybe abstract at the beginning, but it's very, very, very fundamental. And as I said, is prerequisite, of course, to 341. And 341 is very, very applications oriented. Once you get through 241, I highly recommend you take 341. I'm telling you, I'm not teaching now, okay? I'm just telling you what's good for you. I know it doesn't may not look that way now, but it will eventually. I had students coming back and telling me, I'm glad you told me that. Okay? Now,
Perfect.
do I get paid extra for saying this?
No,
there's no
No?
extra. It's just
Or do
the
I get
payment is,
paid,
no.
period?
I'm sorry
No,
you thought you were
again.
getting
Okay,
paid for
that's
this at
okay.
all.
All right.
Well,
well, the payment is this to the students. We like to pick on Dr. Balanis because he has a fantastic sense of humor, but he is a treasure to the department
Yeah.
and the student and we appreciate you taking the time to talk to
No,
students
I'm
at this
telling the
level.
truth. I'm not having, this is no humor. This is telling the truth. You know, and again, as I depart, okay, from this lecture, and I mean it, I haven't said this in public, okay? The staff at AS in electrical engineering, okay? I never had a problem with any of them, okay?
Except for me.
37, to be exact, 37 and a half years, okay? We were very small initially, but then eventually very large staff, many. I had, and I go back to visit, and a lot of times to see and talk, joke, whatever you want to call it, with the staff. Okay? No. This is the honest truth. I'll take my word.
That's so nice of you to say. We love
Well,
it when
send
you
me the
visit.
check in the mail, please.
Yeah,
Got
it's on
it.
its way.
I'll send
It's
that
on
right
its
out
way.
today. Mhm.
Okay.
Can I make one statement to the online students? So we actually offer 241 in the traditional spring, fall 15 weeks. And I know you can take it over summer, but I would encourage you to take it in fall and spring to get the benefit of the length of the class. As we've said, and as Dr. Balanis has said, it's challenging at first, but I think if you're trying to squish it into an 8-week situation, you might cry. So
Yeah,
just
thanks for that tip. That's
Yeah,
it's important
yes.
to plan ahead.
Listen to the staff. You see some of them. I'll see their faces over here as I'm giving this presentation. Listen to them. They didn't come yesterday. They didn't join ASU electrical engineering yesterday. They've been around for decades. Okay, I know them because I had to put up with them.
Well, thanks. We
No,
should.
it was a
should,
joy, and I'll go back, to see and talk and joke, maybe a little humor once in a while with the staff. Yes,
Well, thank you, Dr. Balanis. You're fantastic, and we love having you around, and we
thank you
appreciate
very
you taking the
much.
time to talk to
Appreciate
the
it for
students.
the opportunity. Thanks for inviting me.
Of course.
Okay.
Students, the next phase is the circuits area. So our second largest, or probably our biggest interest area, and our presenter for the circuits area is the area chair, Professor Jennifer Blain. So Professor Blain, thanks for being here today, and we'll pass it off to you.
Let's see if I can share my screen. Okay, am I sharing okay? Does that look good?
There you go. Yeah, we see it now.
Okay,
Perfect.
so this is a really hard act to follow. Professor Balanis, I'm your big fangirl. This is like the Mick Jagger of electrical engineering. So I'll try and live up to following your excellent presentation. But I'm here to represent the electronics circuits faculty. I do want to say Professor Balanis is correct. You do want to have a really good foundation in electromagnetics for any of the areas. And you'll even see, I know my pictures that came from me have some antennas on there. So we do definitely want to see a good solid foundation of the basic electronics class that he was discussing. So that's important for everyone. So definitely agree with that. All right, so I want to talk to you guys about what are the focus areas we have for circuits, what kind of specializations we have, who the faculty are, and I hope I've gotten all the new people, what applications there are for circuits and research that we do at ASU, and where circuit designers or circuits people can find jobs once you finish at ASU. So the basic areas that I'm going to describe in circuits are analog circuit design, digital and VLSI circuits. I'll talk a little bit about microsystems are usually called MEMS, but they're just kind of microsystem devices. I'll talk about some of the emerging devices and circuits, as well as the RF and microwave systems and integrated circuits. So we have quite a long list of faculty. We've really grown since I came here. It seems like we've grown, I don't know, maybe 40% or something since I started here. So we have a lot of faculty across the area, the areas in VLSI and digital. We have Professor Chakrabarty, we have Professor Fong, we have Professor Chalbria, Zhang, Wang, and Li, and Gu. In analog, we have Professor Bertan, Bakaloglu, and Professor Kiai, Ozev, and Sanyal. We have quite a few people that I would say are in the emerging devices and circuits, Professor Ali, Barnaby, Marinella, Professor Jen, and then in the MEMS and bioelectronics are myself, and we have a newer faculty, he joined pretty recently, Professor Shandi, and then in the RF and microwave circuits, Professor Kiai, Kitchen, Dracopoulos, who was mentioned previously, so he's kind of crosses over. And then I'm not even going to make an attempt. I don't know if Lynn or someone can pronounce his name correctly, but Professor Said.
Yep, you said that exactly right.
Sorry, I'm sorry. I should really learn.
I think it's Zenolabadineza. I always mess up the end part.
That's a great attempt. I can't
Thank
confirm or deny. So I'll say the vast majority of our circuits faculty are located in ISTB4 on the 4th and 5th floors. I'm actually not over there. Professor Shandi and I, who do more of the bio stuff, we're in biodesign, but the vast majority are over there. I think most are on the 5th floor, some on the 4th floor. And there are tons and tons of applications. You guys are going to probably be able to name even more than I can. We have so many things that are electronic in our lives these days. From the car that I drove here has tons of electronics. I drove an electronic EV here, as well as all the instrumentation. If I look across my desk, I see almost, I don't know, probably 30 different things that have circuits in them. So anything that you see around you that has some kind of electronics to it is going to have a circuit inside there. We can talk about wireless, which also, again, goes back to the electromagnetics, but we have lots of wireless things, including the computer and the internet connection I have to talk to you. Satellites were mentioned before, that those also have circuits. So there's a kind of that overlap between the different disciplines. I mentioned automotive, aerospace, and then biotechnology, which is what I work on. And I'm sure there's so many more applications you can think of. Oh, security as well, I have on here. But I'm sure you can think of more. Anything really electronic, that you see around you is going to be present sort of, at this point, it's really ubiquitous in our lives. So then for the classes that you're going to take, of course, that those fundamentals that were mentioned in the previous discussion by Professor Balanis, those basic fundamentals in physics and mathematics are super important. EEE 202 was also mentioned. So that's another one that you're really going to need those foundations to be really solid to get into the real coursework. And that starts out with 333 and 334 as well, and 335. So those are your kind of basic courses that everyone is going to want to build onto. So those will really prepare you for the more specializations. Once you have those three courses, which are the VHDL, that's sort of being able to program so that you can design a circuit. So using more of that automated design that has become really prominent these days. And then this 334, you're going to start learning about diodes and transistors. Those are the fundamental computational units that you have in a circuit. And then 335 is going to get you a little bit more into the time variance of circuits. But really those two kind of go together, 334, 335, those build on each other. Once you get through those courses, you can start to kind of diverge into more analog courses. And just as a reminder, so analog courses are courses where your currents and voltages, you're interested in the magnitude of those, and you use the magnitude of those values for computation or for generating some kind of output. And then the digital courses are going to be more like the traditional 0 and 1 kind of computation. So your Boolean logic, your computers, things like that, those all use those kind of 0 and 1 values. So you can split off between those two things into some of the courses. And then each of those will have that 400 level course. And so that's going to be the more advanced versions. 433 is the analog course. You're going to start to use more of the tools, cadence, things like that in those courses. And then the 425 is the digital version. So 433 analog, 425 digital. And then you're going to go after that, if you want to go into the graduate level courses, those are each followed up by a graduate level version of the course. And that's going to get you a little further into the design, a little more knowledgeable, and that's going to better prepare you for some of the jobs that you might be looking at or in a master's program. And I'll echo what I heard in the last, is that a master's degree is just a no-brainer these days. Really, you can do the 4+1 program here, which is phenomenal. It's a great way to really improve your marketability when you're looking for a job. So I can't encourage you enough to really consider at least doing the 4+1, if not doing a little longer term master's degree. And so this is where you can get those courses that are going to build up your knowledge base to have more capability for the specific jobs that you might be interested in. And then if we look in the analog track, you can learn things like analog to digital converters and other types of converters. We have some of the classes that are high speed. So those are the RF or the high speed serial links, the RF amplifier transistor courses. So those are all going to be, looking at some of the very high speed circuits, which we need nowadays. Of course, we look at very fast computation. And then there we have bioelectronics. That actually, I should have updated that. That is the 521 now. That's my class. I should have updated it, sorry. As well as the symmetric VLSI taught by Professor Song. And then in the digital side for the advanced courses, we have synthesis, and that's going to be, again, using more of that computer programming to design circuits. We have the advanced VLSI course, architecture, modeling, computer architecture, and I do need, there are a few more that should be updated, but we have a lot of courses. Some of those are getting more into the AI, machine learning circuits. So lots and lots of circuits. If anybody has questions, I'm happy to talk to you. But a lot of those are really going to follow the ones that I've just discussed, the 400 and 500 level courses that are in white. Those are really important to get you started on your journey through the advanced circuits courses. Okay, so then some of the more specific applications we have. So this is the terahertz electronics. So some of these, I have specific faculty associated because they gave me slides, so I want to acknowledge them, but we do have more than one faculty who work in these areas. So I just want to mention it's not just one person, but just acknowledging their contribution. So a lot of the terahertz, meaning 500 gigahertz or more circuits, those can be used for specialized cameras and imaging, high frequency circuits and circuit testing, on-chip antennas. So lots of different applications for both medical and security or even non-destructive imaging, telecommunications, other imaging applications, and radar. So this is really, again, a little bit of overlap between that electromagnetics and circuit design. Another application is in millimeter terahertz and photonics. So this is looking a little bit more at some of the non-traditional integrated circuits that have more of that photonics angle to them. But again, over on the left are some of the things that are very similar to the previous slide. So the communication radar, imaging, spectroscopy. And then some of the microelectronics for space require radiation hardening. You'll hear that again. Cryogenic electronics, radiometry, radar. And then in the photonics area, there's communication, sensing, photonics assisted electronics, where you're using both the electrical and optical transmissions, sending, receiving information across chip or between chips. Research in VLSI itself, as be a little more traditional, but those do have applications in radiation hardened circuits, especially for space applications. Low power, high performance. Of course, we all want to have that in our phones and electronics. Ultra low power, harsh environment VLSI systems, secure systems. Ensuring that your circuit is secure in the design itself. And there are tons of opportunities for advancement that are going on. We have a lot of faculty doing research in this area. Again, with the radiation hardened design, high performance computation, being really low power, microprocessor designs, secure circuits, low power cache and MMU design, and then multi-core processors and programming. That's we're definitely growing in that area. And those are going to lead you to the more traditional kind of employment that you would think of. So AMD, Intel, Qualcomm, Microchip, Freescale, MRDC, and TI. So definitely those are more kind of what you would say traditional electronics. One of the other areas that some of the other faculty, and I work in this area as well, is neuromorphic computing. So what that means is you're trying to use circuits and integrated circuits to compute in a way that's inspired by the brain. So if we look at the brain, it's one of the most efficient systems out there. We've evolved for a long time to compute, right? To process information efficiently. So this area of research or of design is really just inspired by the way that the brain works. We have some processing in memory that's going on. So Professor Fung is one of the people who works in this areas. So that is taking structures that are more traditionally thought of as memory and being able to actually do computation in the memory of the computer itself. I don't want to take a ton of time. I want to be cognizant of time to get through all of this because we've got so much. But I'll be happy to talk to anybody who has questions about that in following up, or Professor Fahn's a great person to follow up with as well. We have power efficient systems and circuits. So of course, anything that is mobile, anything that we want to carry around, we want it to be very power efficient. So we have a lot of people working in that area, trying to decrease the size, decrease the weight area, power and cost, but still have really high computational power, because everybody wants to watch their video and do all their things on their phone. So it's a really important area of design. And some of that does involve non-traditional devices that go beyond just the traditional silicon semiconductors to more hybrid technologies. Heterogeneous is what we usually call that, or different semiconductors as well. So the gallium nitride is one example of that. And this also goes into space, so for satellite communication or other applications. So this one comes from me, and I will get so excited if anybody asks me questions, but I do a lot of things with human health. So one of those was actually during the pandemic. So you can see one of the systems that I created in the photographs on the lower, I don't know, is that your left or right? But you can see the system down there. So I can create things, for instance, that in the palm of your hand can really tell very accurately whether you have COVID. So a lot of the in-home tests, you have to kind of be sick before you can detect it. We detect very early. I've gotten to go to India and detect cervical disease in people. I really love what I do, and I'll get really excited to talk about it. We do other applications in looking at the nervous system or trying to detect different molecules in the body. I also do implantable devices. This is where I overlap a little bit with some of what was said by Professor Balanis. So we put things into the body. A lot of times that's in the brain. That's a big focus area for me, but we also do cardiac and other implantable devices, wearable devices. And of course, we don't want these to have a wire. You don't want to be plugged into a wall. So we have antennas that we use for that communication through the skull, so we can be fully implantable. We also have to be squishy, because your brain's squishy, so we want to be just as kind of squishy as the brain. We make things that are transparent so that the surgeons can place them properly and suture them in. And we do this all with no wires, no battery, and no really active. Some of these are no active components. Some of them are, but we're able to do neural recording and stimulation. We do a lot of MEMS devices too, pressure sensing, actuation, things like that. Some of the other people that work in this area work on a lot of sensors and sensor systems. So these are all the things, and a lot of those are going to sit in your phone, for instance. Anytime your phone automatically flips the screen so that's in the proper orientation, or the way that it knows, a lot of the things that it knows are going on, those are all sensors that are embedded in your phone. And I think at last count, there's 40 some sensors in the phone that I'll have to double check. I think it might get a new one recently, but lots and lots of sensors in there. And these can not just be in your phone, but a lot of other applications that include, determining different types of physics. So do things move mechanically? Is there something that's temperature, changes in temperature, changes in molecules, all different kinds of physics, and then transducing those, or sort of converting the energy from one type of physics into electronics so we can read it out on an electronic device. So lots of applications there with the environment, with geology, astrobiology, all kinds of stuff with NASA is very interested in this. Any kind of detection of different things like the gas and oil. So it's just a huge range of applications here. Radiation hardened gets back to the space. So if you want to do things that go into space, they have to be what's called radiation hard, or meaning that they're not as susceptible to radiation damaging the devices or the circuits. So that design in particular is a very specific type of design, because in radiation, you'll get damage to the crystalline lattice, and that kind of messes up the way the devices behave. So this is another important area of design. There are lots and lots of emerging devices and circuits that are happening. So some of those have to do with new materials. Some of those have to do with making transistors in different geometries than we're used to seeing. So some funky shapes that really help with the the electromagnetic fields that are existing in those transistors. Some of those have to do with the way that things are placed with each other, making little tiny computer chips that all kind of work together harmoniously. The brain inspired stuff, trying to make like the physically unclonable functions. So that's creating hardware that other people can't copy, that you know is the actual original device that you were intending to use. So tons of stuff going on in that space. And so that's kind of a really quick fire hose. And I know it was just like so much so quickly. And I know that people, including myself, be happy to talk to you more if you have interest in anything specifically. But I'm supposed to do this in a really short amount of time, and I think I'm probably over already. But where do we find jobs? So these are some of the lists of places that people go. Intel, I know I've sent my graduate students to Intel, Raytheon, Honeywell, General Dynamics, Boeing, IBM, Freescale, Microchip. One of my postdocs is now got a really nice position at Microchip, Orbital Sciences, others. I send people to Medtronic, GE Life Sciences. I'm more on the medical side, but tons of places to work. These are some of the top 50 companies to work for. This is a little outdated. I should update this, but we have people that go to NVIDIA, Cadence, Google, Intel, Qualcomm, Burns McDonald, lots and lots of different places. So definitely there are lots of jobs out there. And so this is a list. This is certainly not comprehensive, but these are places that our students have gone. Definitely I see a lot of places. I've sent people to Intel, I've sent people to NXP, sent people to TI, Medtronic, like I said. So lots and lots of places that all our faculty are able to send our students after they do either the undergraduate, master's, or PhDs in our labs. So there are lots of opportunities for you in this area. And this was a older article, but I thought I'd leave it in here. So this is just kind of encouraging that there are some courses that are not easy. The one that Professor Balanis described, there's a lot to get through in your education, but it really does pay off. These are great jobs. There are a lot of people who are making good salaries. There are lots of jobs in the Valley. In particular, we have a lot of opportunities here. So it's a great profession to be in. And then there's some of the compensation broken down a bit. So people make, nice salaries when they get out of here, able to have sustain a pretty good lifestyle. And there are definitely lots of opportunities to move up. So I see that my students work there, maybe, 18 months, they're in they've moved up. So lots of good opportunities for you guys in this area. Lots of opportunities. And I think this is also old. I should update this because we've got a lot of new companies here. TSMC is here. I think I'm gonna stop because I know I'm over time. So I'm not horribly taking over too much time, and I leave some for questions, but there are amazing opportunities to work in this area. I enjoy so much what I do. I get to make things that help people. And I just find a lot of satisfaction in what I'm able to do and how I'm able to create things that really improve lives. So I think with that, I can ask if there are any questions. And I'm sorry that was kind of auctioneer speed and just a fire hose, like I said, of information.
No, thank you very much for the presentation, and special thanks for the personal connection. Sometimes the students often were focusing on careers and salary, which is very important, but you added some personal passion into it. So we really appreciate that. Students can do both, right? So we do have a couple of questions. I did notice a student here asking, are there MEMS courses in the middle of digital analog? I believe there are. Do you have comments on that?
Actually, so the MEMS classes, so I haven't taught that in a little while. So definitely reach out to me if you're interested in that, but that actually doesn't require it was sort of put in the middle because it doesn't fall under one of those categories. That's one you really don't need a lot of advanced circuits for. You kind of just need to know what an amplifier is, and that's pretty much it. What I will ask you to do in that class is remember a lot of your physics. So because MEMS are really transducers, they're going from one physics to the other. You have to remember a lot about mechanics, a lot about fluid dynamics, a lot about the thermo stuff. We have some optics. So it's really just recalling a lot of older physics and then trying to put that into the context of the sensor devices.
Thanks. And thanks, Lynn, for reminding people on March 5th, we'll be doing the graduate school one to talk about accelerated master's programs. And online students sometimes don't realize that's for them too. So 4+1 is kind of the old language that was talked to for traditional undergraduates, but it's really not just about completing an extra, doing it all in 4 years or 5 years. It's really about sharing courses between the 2 degrees. So think less about the time and more about the efficiency of sharing classes. There's another comment in here. Oh yeah, Lynn, the NVIDIA is doing a great job with internships with high pay. Other comments? Yes, we'll have the recordings on the website. We have a quiet group today, not tons of questions today. So there's no other questions for Dr. Blain while she's here? I think it's cold outside and everybody's a little chilly.
I would just really encourage you guys, go and talk to faculty. We really enjoy talking about things. We've got a lot of people who came from industry. So if you go and look at our biographies, not myself, I worked at a hospital rather than going to industry. But there are a lot of people who worked in industry before coming here. And we have people who are here who have worked in industry, who are not tenure track faculty, but other types of faculty who have lots of industry experience. Talk to them about what their life was like and what their experiences working in the Valley, because I think it's such a great place to be an electrical engineer.
Yeah, well, I think that's probably it for, we're getting a couple of thank yous in here. So thanks for being here from the students and from us. And we know you're busy. We appreciate your time. So thanks for taking time for this.